given local community size or distance from whatever mainland you're under consideration, or the Hubble neutral theory, which generates a similar expectation for the abundance distribution. And we'll the gimme-sad model is a forward time, backward time process. So we run a community assembly process forward in time, and then backward in time generate genetic variation based on the forward time results. And so the forward time model is based on this work of Rosendale and Harmon, 2013. So essentially, this is you have a local community which is of fixed size and which is connected to a much larger regional pool of species. And so the way the model runs is at each time step you sample one individual randomly to remove, and with some probability you fill that vacant niche space with an offspring of another member of the community randomly sampled, and with 1 minus that probability, then you have an immigration event where you sample a random individual from the regional pool to replace. And so then you just do this over and over and over and over and over again. So as we do this, we keep track of, in each simulation, we keep track of the changing population sizes of the changing abundances of each species. And we also keep track of the age of the species because we know when each species entered the local community, because we keep track of the time of the colonization events. And so then we can use that information backwards in time to generate genetic variation under the coalescing. So essentially, it looks like this. We have the meta-community. This is like a barrier, some kind of barrier to dispersal, so an ocean or a desert or something. Individuals enter the local community, there's a process in the local community, and then we get genetic variation at the back end. So in forward in time, here you can see this is linked simulations where we have the rank abundance distribution here, and we have genetic variation and genetic diversity. So this is a histogram that summarizes the genetic variation in the local community, and all you need to really see right now is that these things are changing and simultaneously. These two data axes are linked. They're generated from the same simulation, and also they change through time. So here, this is the beginning. You can see there's few species, and as you march forward in time, you accumulate abundance, you accumulate species, and similar things happen with the genetic variation. I'll show you. So this is results of some simulations. So we have this measure of time, which we call lambda. So you can think of lambda of 0 is a brand new community, like an island just came up out of the ocean, there's nothing on it. And then a lambda of 1 is full, we call it, it's turnover equilibrium. So you can think, so this is late stage assembly, this is early stage assembly, and so you can see this is a bunch of different simulations. And what you're looking at here, so it's early, middle, late. You can see that the numbers of species in the community kind of march forward, and the abundances kind of march forward in a similar fashion. You accumulate abundance species, and we can look at something similar for the genetic diversity. So here again, this is brand new community, just rose up out of the ocean. Here this is turnover equilibrium, and you can see kind of similar pattern where genetic variation accumulates in the simulations. So now up to this point, we're only looking at the abundance distributions and genetic diversity in isolation. But if you look at we can look at the joint abundance genetic diversity the correlation between abundance and genetic diversity. And what you can see here, you can kind of blur your eyes. Each of these lines is a regression from a simulation. And so the darker the line is, the younger the community is. And so what you can see is that as the community ages, as the community gets older, the correlation between abundance and genetic diversity increases, which I think is an interesting result. So let's see what we can do with this. So we have a sample of community data from the spiders of Union Island from again, Brent. There are 65 species, 1,200 individuals, 600 of them sequenced or 600 base pairs of mitochondria. So in this case, we're going to ask the question, what can we do with, this is just genetic data. So what can we do with just genetic data? Can we estimate the abundance distribution of the local community using only the genetic variation? And here's the results. So the black line here is the posterior distribution. So this is our posterior estimate. The red line is the observed. And so you can see, in the blue line, this is the prior, and this is the 95% HPD. So what you can see is we're doing a pretty good job of being able to estimate the abundance distribution using just the genetic data, which is really cool. So I told you about this model that I created, abundance and genetic diversity. Abundance and genetic diversity in the community there's a correlation between abundance and genetic variation, genetic diversity, but the correlation is mediated by time. And we can estimate abundance structure using just the genetic data. Okay, so now we have a good neutral model, something to build. We have a foundation that we can build stuff on, but what I want to know is, can we expand this model to really account for more of the action that's going on across the levels of biodiversity? And so that's what we did. And we call this massive eco-evolutionary synthesis simulations. So we're now generating, this is a joint model of abundance, genetic diversity, and trait values in a phylogenetic context. So there's a cool logo, which Ariana, so I can't take credit for this. Andy designed it, and Ariana actually did the drawing, and I just paid for it, so I'm like the executive producer. So now we're really literally, we're going to build on the foundation of GIMESAT, and we're just going to add some new things, see what more kind of behavior we can develop out of it. So the first thing that we will add is the Idaho 3 here. Really, this is the Idaho 1. Megan Ruffley was the chief collaborator on this stuff. And so we're going to introduce some non-neutrality. So in the last model, I said, well, in the local community, everything's ecologically equivalent. You just sample one thing based on, and the probability that you would sample any individual is a function of its proportional abundance in the local community. Now what we want to do is we want to say, okay, now imagine if the species have traits, and if the traits interact with the environment in some way. So we can imagine that there's like an environmental optimum, and the proximity of the trait value to the environmental optimum would have some effect on how likely the individuals from a given species are to be sampled. And so this is an equation thingy here. It does the magic. So we have an environment. We implemented an environmental filtering model where all the species interact with the environment. There's also a competition model where all the species interact with one another. So your probability of survival is a function of your distance from the trait mean in the local community. So the more different you are, increases your survivability. We have talked about having both of these things operate at the same time, but it hasn't happened yet. And then we also implement a speciation process where the whole model is all the same, except for at a birth event, at an event where a local individual of a given species is going to, there's some probability now that a new species will be generated at that time. And so just implements a local speciation process. And we worked with James Rosendale and Ron Paul on this stuff. So now we have different kinds of assembly functions. We can have a purely neutral model. Here in this cartoon, now we have the barrier dispersal. There's an additional barrier which operates as a filter. In this case, this is an environmental filtering model. Or we could have a community which is primarily composed of local assembly. So if speciation in the local community is very important, then we can construct a model of this. Essentially, we have now, instead of 0 knobs, we have 2 knobs. We have like an ecological strength knob where we can turn up or down how strong ecological interactions are, and we have a speciation knob where we can kind of tune how important, we can turn up or down how important local speciation is in the community. So this is the same kind of cartoon as before. We just have a couple new things going on. Again, we can get the same kind of like temporal dynamics of abundance distributions and genetic diversity. Here I'm going to show you just a couple of results. So in here, the blue is the neutral, the yellow is filtering model, and red is competition. And so this is the normalized Shannon diversity, which is essentially a measure of evenness in the community. So what you can see here is that neutral communities tend to be more even, which makes sense because you will have, in competition models, you will have more dominance, right? Because some species will be more able to suck up environmental space because they're more fit. And here, just looking at variance in local traits, so this is exactly what you would expect. In neutral communities, the variance in local traits is kind of in the middle, and with competition model, there's higher variance in local traits, and with the filtering model, there's reduced variance in the local traits. It makes perfect. When I saw this, I was like, yep, that's how it should be. So good thing the model, at least that part of it works. Okay, so now what can we do with this? So here, first of all, we want to ask is, can we, using genetic data alone, can we distinguish between neutral models, filtering models, and competition models? Can we distinguish these? So we used a random forest classification process where you just generate a bunch of simulations, you know what model you generated your simulations, you train the random forest, and then you interrogate it with simulations that you didn't train it with. And so using just genetic data, here this is a confusion matrix, which is basically reporting the results of the random forest cross-validation procedure. And what you want to see is here, like if the true model is neutral, you want the random forest classifier to say, oh, that's a neutral model. So you want this to be closer to 1. So the darker the square is, the better the random forest is doing. So here, if you're using just genetic data, it does a really good job of telling the neutral from the non-neutral models, but between the non-neutral models, it can't tell the difference. Okay, so now if we have genetic data and trait data, still the neutral model, you actually get improved resolution to distinguish between the competition and filtering models using the trait data. So now, not only do we want to classify, we might be interested in estimating parameters. So in this case, this is a cross-validation regression procedure. For example, just for 2 of the parameters, there's a bunch of parameters I'm not showing you here, but for equilibrium and for migration rate. So this is migration rate into the local community. This is random forest regression. So here, again, this is just tons of simulations. You know what the real value is because you created the simulations, and then you try and you ask the random forest regression procedure to tell you what it thinks the real value is. And so what you want to see is everything falling on this red line, right? The simulated value and the estimated value should be close. And in this case, what you can see is that the random forest regression is pretty good at estimating lambda. And still, when I see this, I'm like, that's pretty good, but it's not great. But it's still pretty good. Okay, so now we're going to look at some results from real data. This is the same spider data set from Brent from GimeSad. We're going to look at this again. Then we have 2 different weevil data sets, one from Reunion, one from Mauritius, and then some trees and some snails. You can see, so this all is genetic data and abundance. This is genetic data and traits, genetic data and traits. So one of the things that we're kind of advertising as being one of the interesting functions of MESS is that there's 3 axes of data. There's abundance, genetic data, and trait data, and you don't need all 3 of those to be able to perform inference. Actually, you can have 2, and then you can perform inference on your missing data axis. So here we're just showing kind of different ways we can do that. So this is random forest. We're just going to classify the communities as being neutral, filtering, or competition. So this is a classification procedure, and the color of the bar indicates what the random forest classifier thinks it is. And so what you can see is that spiders are looking very neutral. And then, from the snails are looking like there's a very strong impact of environmental filtering. And then the weevils maybe a little more equivocal there. And now we can look at parameter estimation. So this is this is the migration rate on one axis, and then the local speciation rate and equilibrium on another axis. And so really I think one of the most interesting things to take away from just this is you see that there's different things going on in different communities on the same island. So you have, this is reunion, spiders and weevils, and there's different community assembly processes happening in the same environmental space. And you also see that there's the same for different kinds of communities, and for different, you can see similar processes happening for the same communities in different spaces. That's, I think, an interesting outcome. Okay, so now we have a multi-scale model of biodiversity that incorporates abundance, genetic diversity, and trait variation. We can tell the difference between the deterministic and stochastic processes. When I say deterministic, I mean like competition or filtering models, and stochastic, I mean like neutral models. And we can quantify the contribution of in situ speciation and colonization to community composition, right? Which is really cool. Okay, so now we're going to kind of expand the scope from looking at just individual communities. Now, well, we want to be able to actually like learn something about communities across the whole landscape. And so community assembly takes place in an environmental context. Here you can just see the depth of seafloor for the ocean. We can, oops. So this is kind of fun. So this is current day. This is last glacial maximum when sea level is 100 meters or so lower. And so you can see, like, for example, look at the coral triangle here, right? Coral triangle, this is contemporary, 20,000 years ago, much different landscape. So in the coral triangle, there's been a considerable amount of recent recolonization in this region. Recolonization, so there should be some interesting dynamics here. What I'm trying to show you here is that we have an increasing volume of remote sensing data with which we can characterize the environmental conditions that a community is existing in. So we can look, here's sea surface temperature, here's mean salinity. So we have a bunch of these things. The marine variables, there's maybe less, and they're less well developed than terrestrial variables, but we still have them. So we can take these remote sensing data. We can take remote sensing data, and then we can sample individuals from a region, and we can extract the environmental conditions that are recorded where we see an organism and we know it to have been. And then we can project this across the landscape and say, well, here's all of the other regions that are suitable. That people call this habitat suitability or species distribution modeling or ecological niche modeling. I don't really care what you call it. It's all kind of the same thing. So Mike Hickerson, this is actually the paper that convinced me that I needed to come work with this nutcase. When I saw this paper, I was like, this guy's a product. So he gathered all this data from Bigfoot and then constructed a species distribution model of Bigfoot. So this is all, the kind of dark color here, this is all where Bigfoot should be based on what we know about its environmental conditions.
I love that.
So you can extend this concept and actually do something kind of similar, where instead of looking at currents, you can look at the genetic diversity within species and correlate with environmental variables, and then do a kind of thing where you project across the landscape to see which communities should have more, or species should have more similar genetic variation to which other species. You can do something like this, where you're looking at like community composition. So this is like the color, this is Queensland in Australia, and the colors here are some indication of like community similarity. But again, this is all kind of like taking community data, taking environmental data, and then doing some kind of like species distribution modeling type procedure. So what I want to do, because I'm interested in genetic variation at the scale of ecological communities, I want to do this for the whole community. I want to gather some samples. I want to take samples of communities, sequence them, construct the the species genetic diversity distribution, and then take the environmental variables, and I want to say, if we have 10 samples from across the coral triangle, can we like project this across, can we look for environmental correlates, or can we take environmental data and look at what we should expect the genetic variation in the community to be across the whole landscape, because that would be really useful. So we did this, working with Chris Meyer and his Indonesian collaborators. We have 10 sampling locations. This is a ton of work. They did a ton of work in the field, and they gathered thousands and thousands of samples per site. Each site has on the order of 100 to 200 OTUs, so this is operational taxonomic units. You can just think of it as species without names, just like groups. So I'm using Hill numbers as summaries of the abundance distributions and genetic diversity distributions. And so I was talking about Hill numbers earlier. So Hill number 0 is species richness. Hill number 1, the Hill number is essentially a summary of how much dominance there is in a community. So if you see a very flat series of Hill numbers, then the community is very even. It's more even. And if the Hill numbers go like crunch like this and go down really fast, that means that there's there's one or a few species that are like very dominant. So I just want to just briefly show this because I think this is really cool. So for what's going on with the other locations, don't really worry about that too much right now. Look at Aceh, okay? Aceh is the green one. This is a good exercise in how abundance distributions and genetic variation distributions record information on different timescales. So look at Aceh. Aceh is the second biggest in terms of Hill numbers. Lots of, for genetic diversity, it's the second most, there's the second highest level of genetic diversity, and look at abundance. Second highest species richness, but then look at this crunch, this huge drop off here in the abundance Hill numbers. And so I showed this to Chris, and Chris was like, well, yeah, we know there's at Aceh, there's this crazy invasion where this one species come in and just stepped on everything, right? So that shows in the abundance, but it hasn't had time to impact the genetic variation, the genetic diversity distribution, which is, I think, a good illustration. Here you can remember this is kind of the progress of the community towards equilibrium. The more correlation there is between abundance and genetic diversity, the kind of later stage it is. This is the real data. This is not the fun stuff yet. I just figured I'd show that. Okay, so here I'm going to show you, I'm going to introduce environmental principal component space. So there's suites of environmental variables for marine environmental variables, and I took all that stuff and just collapsed it into 2 principal components. So this is it's a way of scaling multi-dimensional data into 2 dimensions so you can look at it. And so this is 1,000 background points sampled from 20 meters, across the whole region at depth of 20 meters or greater. So this is random points that are at a reasonable depth that you might expect to find corals at. And you can see that, in fact, these are coral-associated decapods. I'm sorry, I got ahead of myself. So this is coral-associated decapod communities. So you can see that the sites that actually have the coral heads that were sampled from are in this kind of, they're particular, right? They're not just anywhere 20 meters or up. They're kind of in a particular area of environmental space. So now if you just look at sites where we know corals have recorded to be, well then all the sampling sites fall well within the kind of cloud of points of environmental PC space. And we can look at what are the kind of primary, we can look at what are the loadings on the PCs, and so this kind of direction is variance in sea surface temperature, mean annual sea surface temperature. This is nutrient concentration and bathymetry, and sea surface salinity. So these are kind of these are the kind of core components of this space. Now we can take, this is really cool. We can take this, so this is all the sites that have known coral records, and now we can color them on the map, and we can actually look at environmental space in a geographic context. So you can see here there's this like pink region here, there's this kind of purpley, this whole like island chain is all kind of in the yellow zone.
What do those colors mean again?
This is its location. These are colored identically to this figure. I'm sorry. So this is its location in environmental principal component space. So I wanted to show this anyway, so thank you for bringing me back. So you can see this long kind of like cloud out here that's kind of like hasn't really been sampled from.
Mm-hmm.
This long cloud out here is here, right? So there's actually a lot of this region, a lot of this, this is unsampled geographic space, it's also unsampled environmental space. So you can use this to kind of like inform sampling strategy for the future. Oh, I should have just done this. Still there. So just looking at kind of the environmental space across the region. What time is it?
You're 2:40.
You're good.
Okay. So now we can perform a similar procedure with MESS. We can use MESS, and we can say what is the neutrality? What is the assembly model that best fits the communities across this region? And you can see there's like a bunch of like I have no idea. But then bang, 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 you have these three here that are like super, super, super neutral. And if you look, if you look where those are, it's these three easternmost sites. And Chris was speculating that this was potentially some proximity to deep water. That was his initial thought. And so, we haven't fully, I have some other things to consider, but we won't go into the details on that right now. Okay, so here, now the colors these are different colors. So now what I did was I took the 10 sampling locations. So this is the first hill number for the abundance distributions for each of these communities normalized to species richness. So the maximum value this number will have is 1, and the minimum is obviously 0. And the bigger the number is, the more evenness, the more evenly abundances are distributed. And so I took the values at each of these sites and constructed a random forest regression machine learning jobber. And did some transformations on the environmental layers, and then actually trained the machine learning jobber to on these 10 sampling points, and then interrogated the machine learning framework and asked given what we know about the normalized first hill number, given what we know about the value at these 10 sites and the environmental conditions at these 10 sites, predict what the abundance structure of the community will be across the whole landscape. And so the color here actually is indicating what the machine learning framework is estimating would be the abundance structure, the first hill number across this whole region. And so you can see here, this is kind of interesting here, even in this unsampled space, what this allows us to do is makes predictions for unsampled locations. So here, even though we don't have samples of this region, we, given what we know about abundance distributions and the environment, we would expect there to be a lot of evenness in these communities. We can do something similar with the genetic data. So here, this is the exact same procedure, but now we're looking at the normalized first genetic hill number. And again, what you can see is like a lot of evenness here, a lot of evenness all throughout this region, and a lot of lower values for evenness here. And I have some guesses about what that is, but I don't want to. Okay? So I don't have my sweet logo for this thing yet, but it's on the way, I think. So I've showed you how it's possible to predict genetic diversity structure across the entire landscape. We can use this to identify key unsampled areas of both environmental and geographic space, right? Like if you want to inform a sampling strategy, it's very difficult to get this kind of information. You want to go where it's going to maximize the benefit for understanding the region. Like this really will be useful. And then, this was kind of my speculations about habitat stability. So like, this is a region where the variance in sea surface temperature is like there's lower variance in sea surface temperature and sea surface salinity values. I think the hydrological regime in this region and the relative hydrological stability in this region is what's causing this kind of like patch of like evenness and diversity here and less evenness over there. That's what I think. Okay, so that's it. So I get to have my fun time. So what I'm going to do first is I want to start by thanking the people without whom my PhD could not have been successfully completed, right? These people make the program run. Joan, Laurel, Kathy, Christine, Marnelli, who's here. Thank you very much for everything, Marnelli. And Anna and Maria. So these people really make the whole thing happen. So I really appreciate all of their invisible labor behind the scenes. I want to thank the herpetology department at the American Museum of Natural History for giving me half a desk and teaching me what the most important parts of science are, which is snacking and lounging. And I will wind up by thanking my committee members first. So everybody who knows me knows that I have this habit of anytime you say something hilarious, I'll write it down in a book or on a piece of paper. So here it's going to come back and bite you all. So this is Andy in his natural habitat. And Andy once said, there's not going to be much opportunity for computation out on the trail. And he also said that spiders are so neutral. I knew I always liked them. And then there's this one picture of Andy, which I always like to show to kind of razz him, and I told him I'd never show it ever again in a talk, but...
I cannot believe it.
Andy getting the old lightning bolt from GW here. Andy, I promise I will never show this picture in a talk ever again. I really mean it. So now on a carnival, natural selection is in your face. Survival. I had to cherry pick some of these because Anna's infinitely quotable.
Yes.
Selection is in survival of the fittest. It's reproduction of the good enough. That's good. There is no science without assumptions. And this is my favorite. I don't care about what's cool. I care about what's closest to the truth.
I love that picture too.
Brian Smith.
Oh my goodness, our video.
Has taught me so much in life, but he has not managed to teach me how to do a sick rail slide. Like this. I gotta loop it, hold on, so you can really get the full flavor. This is Brian Smith, ladies and gentlemen, shredding the gnar. So in case you wanna,
Oh my God.
in case you don't believe it, you can see that his style has improved a little over the years, even though he doesn't appear to have aged like one day. What is this, like 1999? You look identical to this. Oh. Dug up this old number. Look at their skin underneath those tattoos. This one, this is classic Frank Burbrink. You don't get anywhere in life doing cladistics. If you're not wrong in science, you're religious. The things that are certain are obviously certain. I always got a little bit of like an embrace the uncertainty thing. And this one's my favorite. I love rat snakes more than I love any human being.
I've been drinking.
But he stood by it.
I know, I stayed by it.
Oh yeah, here's the good one. And now,
Oh my God.
time for the big guy. You all know, Mike's list of quotable quotes is longer than anybody else's, so really this is the cream of the crop. We worship the coalescence. I had to write that on. and we go like we worship the coalescent. This one I also use a lot. Taxonomy is a bit above my pay grade. I told one time Emily McTavish asked me a question. I was like, taxonomy is above my pay grade. She got really mad. I didn't think it was funny. In any model-based approach, you're going to have to make some sacrifices, which is true. I'm trying to be the squeaky wheel. That's classic Hickerson. This one's classic too. It's stake 30.
This is so, oh my god, Mr. Lowe.
So now really, whoops, I forgot there's a couple more pictures.
Oh, wow.
So now here's the question that we've all really come to search for the answer for. Were they separated at birth? Let's zoom in and take a closer look, okay? I think the evidence at this point is inconclusive, so we'll just have to leave this mystery hang. So thank you very much, everyone. Thank you for coming.